Hi, everyone. Welcome to the webinar. Thank you for tuning in this afternoon. My name is Garrett, and I am joined today by Dave, Head of Client Services. His video will be turned off throughout most of the event, but he will jump in from time to time, and that's just so that we can see the farm in full view behind me. So to kick things off, I'm standing inside the Greenery, which is an atmospherically controlled, tech-connected hydroponic farm built entirely in a 40-foot shipping container. In these 320 square feet, we can grow hundreds of varieties of produce, all in the vicinity of where it's being consumed, which drastically shortens the food supply chain. Today, we're going to discuss water conservation within the Greenery, how our system works to provide nutrients to our crops, and most importantly, how this system allows you to grow food anywhere in the world, even in drought-prone areas. So who am I? Before we dive in, a little bit of background on myself. I am a second-year master's student at Duke University. I'm studying the intersection of business and the environment, and I'm specifically interested in food systems, high-tech food production, and how to mitigate food waste. I spent the last year working on the Duke campus farm, which is a small 1-acre learning lab where we grow food for the community and for the Duke Dining Commons. It's here that I received most of my training in the different aspects of food production, so sowing, harvesting, pest management, identifying water stress, soil science, and the like. Before moving to North Carolina, I worked for the University of Southern California, where I had a range of job responsibilities. On the one hand, I built a closed loop aquarium system, which has many similarities to the freight farm system. And it was also my responsibility to take care of an aquaponics system, in-ground garden, and other sort of lab animals and living specimens. However, the coolest part of my job was feeding cafeteria food waste to fly larvae. When the fly larvae were fully developed, we could harvest them and feed them to chickens and to aquaponic fish, which effectively closed the loop regarding food production and consumption. Finally, as an undergraduate, I studied marine biology, and during my degree, I had a lot of exposure to research and reading and writing scientific papers and sort of learning a lot about the scientific method and how to do it right. So we want to share some water usage facts with everyone because it will underscore the importance of water conservation and responsible water use. So first, each person consumes 2,000 to 5,000 liters of virtual water every day. And we know that we should be drinking about 1 to 3 liters of water a day, but virtual water is the total sort of theoretical amount of water used in growing, harvesting, cleaning, and processing your foods. So not just the water directly going into the ground to the roots. So a much bigger number when you expand sort of the scope of water use. And then in a 2010 study, we found that, a study found that the agriculture sector as a whole used roughly 70% of all freshwater withdrawals. So in North America, we're a little bit better. Of our freshwater withdrawals, about 40% is diverted to agriculture, while in countries like Africa or continents like Africa, the average is as high as 81%. So it really depends on the climate there. The amount of water used to produce a farm's worth of lettuce in traditional sort of open field soil-based agriculture is just shy of 1 million gallons a year. The Greenery, on the other hand, uses only 5 to 10 gallons a day, which comes out to between 1,800 and 3,600 gallons per year. So that's 0.2 to 0.4% of the water used as conventional agriculture. And then there are the secondary implications of water overuse, which are runoff, erosion, leaching, and harmful algal blooms. When surface runoff happens, it carries organic matter and topsoil with it, which are the top 2 layers of the soil and the most important components for along with it, the fertilizer that farmers add to the field. So when this fertilizer and this topsoil enters nearby storm drains and rivers, the additional nutrients can trigger eutrophication, which in turn can lead to a harmful algal bloom, which is basically an exponential growth in the population of photosynthetic algae in that waterway, which themselves can either produce harmful toxins or can indirectly harm the ecosystem and all inhabitants sort of down that waterway. So briefly, what is hydroponics? Hydroponics is defined as growing plants without soil. And there are many ways that different people sort of abide by this definition. As a result, the plants primarily get their nutrients from the water, which contains the liquid fertilizer. And then the growing medium, the actual sort of structure that plants grow into, can be many things. In our case, we basically use a peat moss plug, which I don't know if you can see that. This is a little collard green head. And so this just holds water. It wicks up the plant nutrients, and it provides a structure for the plant roots to anchor into. So in the greenery, we use two different types of hydroponic systems. We use ebb and flow, and we use drip irrigation. Ebb and flow is used for developing seeds into young plants called seedlings, and that system is just out of view just below me. The seedlings live in trays, which are situated into troughs or shallow basins, which periodically get flooded and drained. And this happens a few times a day. After 2 to 3 weeks, the immature plants get big enough that we can take them and we can transplant into our drip irrigation system, which is behind me. So here we have one of our panels, which has a bunch of beautiful collard greens in it right now. And we can see that there's 5 vertical channels. So the drip irrigation system comes in, the pumps pump it in from overhead, and gravity takes the water down past each plant. Special wicking strips within each of these channels holds onto the water. It guides it towards the plant and the plant roots, and it prevents the roots from drying out between watering periods. And so some other features of the system include air stones, which keep the water oxygenated and all the nutrients well mixed, as well as specialized sensors that continually monitor things like pH, temperature, and the nutrient profile. So these probes work in conjunction with a software that automatically can adjust pH, temperature, and nutrients depending on the farmer's preference and how they set the system. Both types of hydroponic systems are designed to collect any remaining water and direct it back to our main tank. Water is only lost in our system through direct plant consumption or through evapotranspiration, which is when they release water through gas exchange with the atmosphere. In fact, some farms are even water positive. For example, this farm over the past 8 weeks has been water positive by almost 80 gallons, which means we could effectively take 80 gallons out of the system over the past 8 weeks and use it to maybe water fruit trees in the nearby area. Now, some of you might be wondering how we get away with growing plants in the absence of soil. So first, to define what soil is, soil consists of 25% airspace, 25% water, a mineral component, which can be a combination of sand, silt, or clay, that being about 45 to almost 50%, and then an organic layer, which is anywhere from 1 to 5%, depending on how good the soil is. So in hydroponics, we're effectively replicating the soil solution. Even though we're getting rid of the soil, we still have the constituent parts. We still have the air, the water, and the nutrients. So how do plants get nutrients? Plants absorb nutrients primarily through their roots. However, they can also get it through foliar feeding, which is when we spray. We don't do it here, but in field applications, sometimes farmers will spray dilute fertilizer to the underside of leaves, which is where they have small openings for gas exchange. In conventional agriculture, plants have these highly sophisticated relationships with different fungus species. And these fungi work in symbiosis with the plant to extend the length and the density of the nutrient absorption network, to increase the density and the length of the root system. So the fungi will go out, they'll branch out from the roots, and they will transfer minerals that they find, such as phosphorus, back to the plant to use. And in exchange, the plant will give up some of the sugars that it produces in photosynthesis as a sort of food product for the fungi. So although there might be similar symbiotic relationships like this happening in our hydroponic systems, it's not as vital for plant survival. And there are 2 reasons for this. One, and I'll stress this twice, soil is static, whereas our hydroponic water is not. So the soil is fixed, but hydroponic water is always moving, always circulating. So in the field, plant growth is mostly limited by the extent of the root network. So the bigger the network, the bigger the plant, the more nutrients it can access in the soil. In other words, nutrient quantity is probably the variable limiting growth. In hydroponics, we can continuously add nutrients and sort of move this water, refresh the water, and make sure that nutrients are always readily available to the plants, making that less likely to be a limiting factor for growth. The other thing is that soil and the soil ecosystem is exceedingly complex with organisms and chemical reactions going on all the time. And these organisms and chemical reactions help to convert organic matter like leaf litter and compost and the fertilizer that's added into a form that is actually available for plants. There are plenty of nutrients available, but they might not be in the form that plants can take them up. In hydroponic operations, however, we use a very soluble solution of fertilizer, of salts that are already in the exact form that plants need them for absorption. So an example would be that despite the fact that iron is super abundant in the Earth's crust, it's often limiting for plant growth. And so in the field, plants have to circumvent this by using enzymes to convert iron from a form that is unusable, an insoluble form, to a form that is usable. And so that is not the case in hydroponics. It's already in that usable form. So when we talk about nutrients, there are nutrients that are good and sort of supplemental to plant growth, but then there are the essential nutrients. So there are 17 periodic elements that plants absolutely need, and they're classified as essential based on a few criteria. So first, the plants need it to complete some form of their life stage. So either the vegetative or the reproductive, that is the fruiting and the flowering stage. So even if they don't need it for putting off fruit, they might still need that element for some sort of ramp up phase where they're growing out and going through vegetation. The element cannot be substituted for another element. So for example, copper and cobalt are only separated by one element on the periodic table, but cobalt is not an essential element, and it could not be replaced in our fertilizer solution for copper, and it could not do the same thing in the plant. The element also has to be required by a substantial number of plant species to be considered essential. Of course, there will always be specialists, there will always be outliers. And then lastly, the element plays a direct role in either plant metabolism or some critical plant compound. For example, potassium is needed for stomata control, which is how the plant exchanges gas with the environment, controls gas exchange, while magnesium is the central atom in chlorophyll, which is needed for photosynthesis. So almost all of the plant, like 92–95% of the plant, is made up of carbon, hydrogen, and oxygen. And thankfully, the plant can get all it needs from CO2 from the atmosphere and from the water. The remaining 14 elements come from the fertilizer that we add into our solution. And so let's see if you can see that. So there are 3 numbers here, 1, 3, and 5. And those are our primary nutrients. Those are nitrogen, phosphorus, and potassium in that order. Those 3 will show up on any fertilizer, be it liquid or solid, for hydroponic use or for field use. And so those numbers represent the percent contribution of that element on a weight basis to the solution. So 1% nitrogen, 3% phosphorus, and 5% potassium. The secondary elements are calcium, magnesium, and sulfur. And together, these 6 elements are collectively called macronutrients because they're needed in relatively large concentrations. The remaining 8 elements are collectively called micronutrients. So in general, macronutrients are essential to build the major building blocks of life, that being DNA, RNA, proteins, chlorophyll, and ATP or energy production. And then the micronutrients are more crucial for things like enzymes and plant metabolism, disease protection, and other sort of chemical reactions in the plant. And then lastly, another way to categorize essential elements is by their mobility within the plant. So this understanding mobility will also help you diagnose deficiencies. So an element is considered mobile if the plant can take that element, integrate it into some structure, and then later on when maybe there's a deficit in the water or in the soil, it can break down that structure, reclaim that element, and then integrate it into a new structure. And then immobile being the opposite. Once it is fixed in place, it is stuck there for the life of the plant. And an example of that would be calcium. So although some elements are described as being partially mobile, essentially nitrogen, phosphorus, potassium, and magnesium are mobile, while the rest are more or less immobile. So now we're going to talk about nutrient measurements and limitations of measuring nutrients in hydroponic water. The industry standard for nutrients or for nutrient measurements is called electrical conductivity, or EC. So EC measures the ability for a current to travel through the water, and it's largely dependent on the quantity of ions in solution. So when we take something like a liquid fertilizer, we add it to the system, the individual components break up into their ionic forms. So that would be like nitrogen, phosphorus, potassium again. And each of these ions has their own charge. That might be a +1 charge or a +2 charge or a -1 or a -2. And all of those individual charges add up to contribute to the EC. So it's a really straightforward and quick measurement to get, but the drawback is that EC is a blunt instrument. It's only providing us one number that's indicating the collective balance of all ions. So for example, using just EC, there's no way to know if the solution has a 5:1 ratio of nitrogen to calcium or a 1:5 ratio, which is a big difference when you're talking about the availability and the ratio of nutrients. So as plants consume these nutrients, the fertilizer will add them back, but they will add them back at a fixed ratio. It doesn't only add back what the plants are consuming, which is really important to understand because even the slightest difference in what the plant needs and is consuming and what the fertilizer is providing will eventually, over long periods when you have a recirculating system, will eventually lead to imbalances. And coming up with a solution to something like that is near impossible because different plant varieties and plant families need different ratios and quantities of nutrients at different times in their life. So when you have all of them growing in conjunction, it's really hard to dynamically address that. So surely you must be thinking that there must be a way to measure individual ions. Well, there are many lab companies out there that design and build equipment for that purpose, and they're called ion-specific electrodes, or ISEs. And they can theoretically do this. However, they aren't built for hydroponics in mind. They're built for lab and scientific use. And generally those solutions are much more straightforward. They're not as complicated and have so many components as hydroponic water. So again, an example would be if you went out and bought a potassium ISE to use in hydroponics, it would be unreliable in a situation like this because of something called interference ions. Interference ions are other ions in the solution that the ISE would have trouble distinguishing from, in this case, potassium. So ammonium, NH4, has a +1 charge, just like potassium, which means the ISE would be looking for a +1 charge in solution, and it would basically add up the potassium and the ammonium together and count them as one. So it becomes unreliable in that sense. And then the last way that we can get really granular data on the amount of each ion, each nutrient in solution is by taking a water sample, and sending it to a specialized lab. These labs will tell you the exact concentration down to the parts per million of each element in your solution. And the main drawback here, besides the fact that you're paying for each lab sample, is that you don't get your water results in real time. So it takes time to obviously ship that sample and for the lab to process it and get you your data. And so maybe that's a week later that you're getting your data. And although that's great and it's really granular data, it's now data that is a week old. So you have to sort of choose whether you want real time, but slightly less precise data, or really precise data, but there's some lag time to it. So we're trying to tackle this issue here at Freight Farms. And one way we're doing that is by doing research and collecting data to better understand how nutrients are taken up by our plants in our system. So we've been collecting dozens of water samples from our HQ farm here and with participating farmers. to map all this data and retroactively see how our nutrient profiles evolve over time over the course of, say, 8 weeks. And this will show us how different nutrients like calcium and iron and nitrogen are moving up or down in concentration over time. So this work will help us hopefully in the future extend the useful life of the water before that imbalance that I mentioned becomes too extreme and farmers need to do a water turnover, basically start from scratch, fill up with fresh water and start the dosing system over. So this work will also help us find the best quantity and the best ratio of nutrients for optimal plant quality and for plant growth. So like humans, plants, yes, they need the right quantity of nutrients, but there is a limit. You can't just keep adding nutrients and hope that everything works out. There is also a correct ratio of nutrients. So for example, in humans, we know that omega-3 and omega-6 fatty acids are good for us, but there's also a good ratio. A good ratio would be 1:4 omega-3 to 6. Often we exceed that one way or the other. And so it's important to keep that in our hydroponic solution to a good ratio. And lastly, how does this translate to help our farmers? So expenses will decrease because the fertilizer will last longer and water turnovers will become less frequent. By reducing the frequency of our water turnovers, the farmer will save time that they could otherwise be harvesting or sowing or out marketing their product to chefs. By optimizing the fertilizer regimen, we can also improve plant health and the plant growth rate, which translate to less waste and quicker crop cycle times. The environmental impact of your farm will also decrease because you'll be using less water and less inputs. And last and probably most importantly is consistency. By reducing the fluctuations and optimizing nutrient delivery, you can expect a more consistent yield and your customers can expect a more consistent product. So that's the end of my presentation. And with that, I think we can open it up to any questions that people have.
Awesome. Thanks, Garrett. We'll just bring Dave back on. My name is Amy, and I'll be helping moderate these questions. We got a lot of great questions, so thank you for submitting all of those. So just to get started, and Dave and Garrett, just feel free to jump in wherever on who you think would be best to answer the question. So one of the first questions we got was, how important is your water source quality? Should you test it before you start growing?
I can start with that one. So yes, it's very important. Either way, it's important to know, and you always want to test your water source before you actually get your farm. If it is deemed kind of unsafe for plants, so the EC is too high or there are too many bicarbonates, we would basically recommend a filtration system, which you can install and filter your water before it goes into your reservoir tanks. At that point, it doesn't really matter anymore. The real important thing to know is whether or not you need a filtration system.
Awesome. Do all plants that you grow require 0.2 to 0.4% of the water compared to normal agriculture methods, or does it range based on the crop that you're growing at that time?
So I guess the long answer to this is that every plant is different and that they're going to uptake different amounts of water. However, the way that the greenery works is that we are actually capturing a lot of that evapotranspirated water. So as plants transpire, they're releasing water into the air. We have a dehumidifier function and an AC that is then recapturing that water and putting it back into our tank. So regardless of the rate of evapotranspiration that's happening or how much water they're uptaking and releasing, as long as our dehumidifier is able to deal with the capacity of the water in the air, the amount of water that we use per day is actually fairly fixed.
Awesome. So one question we had was a common complaint heard about hydroponic systems is that because you aren't getting the rich biodiversity of soils to build a robust flavor profile and are only using a liquid soil solution. So hydroponic veggies tend to be more mild in flavor. And this person is just very interested in what we do to address flavor when using hydroponics, or if there have been any experimentation with this.
So what I would say, and I'd love to hear Garrett's thoughts on this as well, but the greenery is your canvas. So you can put whatever you want into your water. We recommend a 2-part nutrient solution because it's very simple. It's easy for people to get started by just going forward with a very basic 2-part nutrient solution. We do have farmers who use a number of additives in their farm. So they'll use bacterial additives such as EM1, which is a Bacillus bacteria. We also use fungi like Garrett spoke about. So this is mycorrhizae. We may even use, some people choose to do a completely sterile system and will just use additives like the nutrients or silica or potentially add in amino acids. There are so many products out there and there are so many ways that you can kind of customize your own nutrient blend. I can't speak to the research that has been done. I don't actually know too much about it. I know that our veggies, I would think, are pretty delicious, but there is potentially, I would say there definitely is a difference between plants that are grown in a hydroponic system versus plants that are grown in a soil system for exactly what this question, the person who asked this question was hinting at. But are there ways to address that? And are there ways to kind of design your plant taste based on what you add to the water? I would also say yes.
Awesome. Garrett, did you want to add anything to that?
I think I got kicked out there for a sec, so hopefully I heard most of it. But no, I think Dave covered it just right.
Awesome. So you talked a lot about water, and one question we got was, is there any wastewater? And how much, if there is, will there be any harm to groundwater environment?
So the system, at least the main tank, I believe holds about 100 gallons. And our farmers might cycle their water, which means sort of starting anew, maybe 6 times a year, every, let's say, 2 months. And the water that's going out, although it does contain nutrients in it, it is very likely being recaptured by the city in normal sort of municipal manner. And with that kind of thinking, just imagine the same way that we get rid of wastewater in other ways, it contains other inputs, and so it can be sort of filtered and treated just like any other sort of municipal water. But a way to reduce that might be that when you know you're getting ready to do a water turnover, you can basically turn off your dosing system for a little while, maybe an hour or 2 hours ahead of that turnover, and let your plants basically soak up the last bit of the nutrients down to sort of reduce that quantity. That way, when you do your turnover, very little nutrients actually leaving the system.
Awesome.
I would add to that really quickly too, that one of the cool features of the greenery that is different from conventional agriculture is that because we know that our nutrient solution contains all of those nutrients, as opposed to spreading a fertilizer out across an entire field, we are actually able to capture that water if we want to. We'll just hook it right up to the drain spigot on the outside of the farm, and that water can be put into some kind of storage vessel. It can then be used to irrigate a lawn or disposed of properly. There is no reason that you would have to empty whatever residual nutrients are left in your tank straight into the environment outside. It can be easily captured.
Awesome. We are quickly running out of time, but 2 questions I wanted to address were, are there organic hydroponic nutrients?
So that's not a tough question to answer. Getting organic liquid nutrients is tough. A lot of fertilizers in general, but liquid fertilizers specifically, do come from mined sources. And the reason that is because it's super hard to get a consistent fertilizer from organic sources. So for example, on the back of the fertilizer that we use, oh, that doesn't have it. Oh yeah, it does. It gives a breakdown, a verified analysis of the amount that's in each fertilizer. And of course, if you're selling a product to anybody, you want it to be consistent, whether you're selling it from this batch or from that batch. And when you make a fertilizer out of organic or sort of natural sources like leaf litter, it's really hard to do that. And so with mine sources, it's just more consistent. I know that the industry and certain manufacturers are trying to do that, but it's solving that problem of consistency.
There's one name drop I put in here, Organics RX. They are a new company out there, but they are producing a specifically organic, all plant-based hydroponic nutrient.
Awesome. And then one last question before we go. I know we're out of time, but can you use collected rainwater if you filter it?
I don't see why not. I think just like with your source water, it'd probably be best to get it tested first and then see if you need to filter it.
100%.
Awesome. Well, we are out of time. Thanks so much, everybody. You had great questions, and thanks for tuning in. We'll be sending out the recording and a few more resources tomorrow. And then if you have any questions, feel free to reach out to anybody on the Freight Farms team. Have a good night.